Oh God. Wow. I have done something. Look at that. That's quite interesting. Let's see. Is there some way okay, I can do that. Okay, we're back to, here. And now I'm upside down. Interesting. Can I flip? Can I go back? Okay, nice. I don't know what's happening in the window. The darkness approaches. Okay. And there's no like filters button. What is happening? Oh, here we go. How did this happen? Oh no. They're not labeled. Oh no. That's definitely wrong. Oh no. Come on. Think of your colorblind customers, man. I'm pretty sure that's wrong. Yeah, my hat is blue. Yeah, I know that's wrong. Okay, normal. Nice. Okay, I'm pretty sure that's right. All right. Page 2, JD's and Littleman. Beautiful, lovely page 2. Trigonometry. This page is all about regular polygons. Alrighty, so let me just specify first up here what I mean by this. A regular polygon, this is any shape. A regular polygon is any shape. That's as long as it's equilateral and equiangular. That's all it's got to be. It's got to be a polygon, and everything about it is regular. It's very boring. Nothing about it is different. Everything about it is the same. So like, for example, a regular hexagon would be this lovely, beautiful, perfect, symmetrical hexagon with everything about it the same. Every side is the same. Every angle is the same. It's very typical. Ready? For example, a regular quadrilateral is a square because all of its angles are the same and all of its sides are the same. It's both rectangular and rhombic. All right, beautiful. In any case, this is what I mean by regular polygon, and there are a lot of these. Also, like you can imagine a pentagon. That's not a great drawing, but same thing, or maybe a heptagon or whatever. It could be any of those. This formula works for all of them. Up here, if you would like, if you're a memory person, you may memorize. Here are some trig shortcuts I've given you. I will not be giving you these on the test, but you are welcome if you would like to use them. And another one in this example is maybe theta is equal to 180 over n. That could help you as well. This way, you basically just like draw this triangle in the shape, do whatever it says to get out what you need. So, for us, the area of a regular polygon is A equals 1/2 the apothem times the perimeter. On a regular polygon, the apothem just goes from the middle straight down to the edge at a 90-degree angle. Okay, that is it. If you can do those things, you're done. So, for example, on number 1, find the area of a regular hexagon if it has a side length of 3 inches. So, here's my regular hexagon. I'm going to draw it kind of tiny because I didn't give myself a lot of room here. It's kind of my fault. There's my triangle. There's the apothem. Okay, and this is where you get this picture from up here, right? There's the apothem, the radius, and then x is the side on the bottom. So like, your polygon would be like out here, and this is just like one triangle out of that polygon. So for this particular case, I'm just going to do the good old-fashioned method. If you would rather use the formulas, that's fine. But in this particular example, the area of a regular hexagon with a side of 3 inches, this triangle here, it has a side length of 3. So here's me redrawing the triangle. And I want to know the apothem because if I want to find the area, that's 1/2 AP. So if I know the outside, then I could find the perimeter. But to get the apothem here, I'm going to have to use some tricks. Ready? And what would be a helpful trick is if I knew what this angle is here in the middle, this top angle. All right? So to do that, imagine drawing all 6 triangles in the hexagon. In the center, the angles must add to 360 degrees. So for this particular instance, it's 360 divided by 6, which is 120, is the measure of each of these angles. And then you can, that is not right. That should be 60. I'm crazy. Sorry, guys. It's 60 for each of these angles. That means half of this in here, sorry, I meant to write A there earlier. This right here, this angle has got to be 30 degrees. Okay. So now that I see this picture, I'm going to redraw another triangle. And guys, remember, all I'm trying to do here is get the apothem. Then I'd be done. So I'm going to redraw this triangle one more time. Now, if I take half of 3, that's 1.5 to make this other piece. And then for the apothem here, if I know this is a 30-degree angle, then I know this must be a 30, 60, 90 triangle. And so this side is 1.5 times the square root of 3. Thank you, formula sheet. Or, better yet, at the calculator, if you want to approximate it, that's 1.5 times the square root of 3. This is about 2.59, or 2.60, really. Alrighty. Sorry, it's supposed to be an 8. About 2.598-ish. So, now that I have the apothem, I'm ready to solve. I know the area must be 1/2 the apothem, which we found to be 1.5 square root 3, times the perimeter. Now, the outside of this shape is 3, and there are 6 of those sides. So my perimeter is 3 times 6, or 18. And then, for my final calculation, I'll plug everything in the calculator. And let's see here. I'm going to use my fraction bar just to make it look like the notes, but you do not have to. You could just put 0.5 here. And I'll put in 1.5 times the square root of 3, close parentheses. Oh, it didn't let me out of there. Let me out, please. Thank you. And then here we have 3 times 6. Look at that. 23.38 for the area of this regular polygon. So, for this final answer here, we'll say it is about, and I do want to say approximately because there is a square root in here. So we're going to say this is about 23.38. Beautiful. And this is going to be in inches squared. So yeah, make sure we include our units there. Box it in, and you're done. Alrighty? So as a general rule of thumb, easy shapes are like hexagons, squares, triangles, stuff like that. Hard shapes are things like pentagons, because you have to use trig on these. Okay? Now, for a shape like a pentagon, you may have to, you may want to rely on these formulas if you do not like or do not remember trig. Of course, you could just watch a trig reminder video for like 3 minutes. It's not that bad, right? So, for example here, what I'd like to do is I have a pentagon. So I'm going to draw it kind of small over here just to give me an idea. And then I'm drawing in this triangle on the bottom. That's this same shape from up here, just because it's the most helpful. All right? And I know that the radius is 16 feet. This radius is on the edge. This is the 16 feet it's talking about. So for my particular problem, here's that triangle redrawn. This side is 16. Now, if I want to solve the area of this polygon, I'm going to need the apothem and the perimeter. Unfortunately, for me, I have neither of those things. I don't have the apothem, and I don't know the outside, so I couldn't find the perimeter. So to do that, you have to trust your gut and use trigonometry. Ladies and gentlemen, to do this, if you would just find the interior angle here again. So for me, this is going to be 360 over 5. Alrighty, and 360 divided by 5, that's 72 to go in the entire top of the triangle. But for the right triangle I'm solving, I only need half of that, so I'm going to divide by 2 again to get 36. Can't believe I just put that in the calculator. So now, imagine like dividing by another 2. Alrighty, and we get 36. So this angle right here in the triangle, that angle's 36. And now I know 16, I want to know the apothem, and I would like to know the outside, which I've called x, but you don't have to. I mean, I'm going to call it x here just to see it. And then check this out. My triangle I'm interested in looks like this on that right-hand side. On the bottom, I have x over 2. Alrighty? X cut in half. Here I have the apothem, and then on the radius I have 16, and I know that this angle is 36 degrees. So I could do a trig problem here to find out the answer for the others. In any case, I think I'm going to find the apothem. That just seems easier. And then maybe I can use the Pythagorean theorem to solve the other one. So, to sum in the trigonometry functions, I say SOHCAHTOA. SOHCAHTOA is a mnemonic that helps us remember which trig function best suits us in any given situation. So, for this particular situation, I'm now going to take my red pen and label. Here, for example, this is the hypotenuse of my right triangle because it's the longest side and it's across from the 90-degree angle. And then here, if I'm standing at my reference angle, across from that angle, this is the opposite side. Adjacent to that angle is the adjacent side. So if I'm trying to find A, that's the adjacent side, and I have 16, that's the hypotenuse, it seems like I'm best suited by CA, or cosine, to write my function. So now, to find the length of A, I simply write the cosine of 36 degrees must be equal to, and in this case, that's the adjacent over hypotenuse, so that's A divided by 16. Solving for A yields 16 times the cosine of 36 degrees. Wham! Just like that, baby. And here, for example, 16 times a cool, calm cosine of 36 degrees has got to be 12.94. Interesting. So this is approximately 12.94. Apothem, done. Now I just need the perimeter. And to find the perimeter, I really need the outside of this shape. Now I know this side is 12.94-ish, and I know this side is 16. So if I wanted to, I could just use the Pythagorean theorem here. That seems a lot easier. So summarizing, I'll say that the Pythagorean theorem for the leg is equal to 16 squared minus, let's see, and that's going to be 12. Instead of like typing out 12.94, I'm just going to grab it from here and then square that whole number and be done with it to get about 9.40. So let's say in the other part of my notes here, I'm going to say like, I found that x over 2 was equal to 9.40-ish using the Pythagorean theorem. That means that x has to be double this. That's because we had to cut the triangle in half, right? Don't forget to do a right triangle. And now we'll multiply back by 2, sorry, I meant multiply by 2 to get around 18 point. This is going to be 80 and so forth. And now we are ready to find the area. Now I know I'm almost out of room, that's fine. I'm going to give myself some room from the other part over here and say that A has to be 1/2 the apothem times the perimeter. Okay, we saw that the apothem was about 12.94. And additionally, the perimeter must be 18.8-ish times, and then we had 5 sides on this pentagon, so that's times 5. And so for our final answer, we'll put that on the calculator. That's 1/2 times, here we have a 12.94. And actually, let me not write that whole thing out. You know what? I'm just going to go grab it from up here. 12.94-ish times, and then we have this number to represent our x times 5. So again, here's the perimeter in total. There's 5 sides. Each of them is 18.8. And then let me arrow to the left. Alrighty, here's our apothem, which you found to be 12.9-ish. And we hit enter for about 608.7, approximately. And I believe this is feet, yes, feet squared. Alrighty, seeing that from that there. Look at that. Okay, awesome. One more question to do, and then we'll try the next page. Let's see here. For the next page, next question. An interior designer plans to decorate a countertop with hexagonal tiles. Each hexagon has 1/2 inch as the side length. If the countertop surface area is 2,160 square inches, how many tiles will be needed to cover the surface entirely? Alrighty, so we have a countertop that's 2,160 square inches. We have hexagonal tiles, and we want to place them over the top. What I think is cool about this problem is it doesn't tell you the length and width of the countertop, and that doesn't change the answer. We're going to get the same answer regardless. So, for example here, If each hexagon is 1/2 inch side length, the countertop surface is 2160. How in the world do we solve this? Well, we know there's some countertop. It doesn't necessarily even have to be a rectangle. Doesn't even necessarily have to be a rectangle. But for this example, I'm going to draw it so. This rectangle has 2,160 square inches on it. Okay? These hexagons have a 1/2 inch side length. So one of these, and now I'm drawing this not to scale, the hexagon would be very tiny because this side is only 0.5 inches. So if I knew the area of this hexagon, I could find out how many I needed by dividing, right? Imagine placing down a hexagon on the surface over and over again. How many would you need? Well, however much area you have distributed out across the whole thing. In other words, 2,160 divided by the area of this hexagon. So with that as my game plan, I'm going to first find the area of the hexagon using area equals half the apothem times the perimeter. Okay, from earlier, I know I've already done this math before. I took half of the side and then multiplied by the square root of 3 because it was a 30, 60, 90 triangle. That's not going to change just because I changed the shape, that's not going to change just because I made the shape smaller. It's still a hexagon, right? So that means this triangle here in the middle, if I was to redraw it, all the same things would happen. This would be 30. The side length would be half of 0.5, which is 0.25 inches. And so the apothem would be 0.25 root 3, or root 3 over 4, if you prefer. And now I can find the perimeter of this shape by doing the following. Or the area of the shape, I should say. We have 0.25 root 3 for the apothem. And then on the outside, if each side is a 1/2 inch, that times 6 gives you 3. 3 inches total for their perimeter. So I'm just going to put 0.5 times 6 for the purposes of the notes. And bam! We'll plug this all in to get 1 divided by 2 times 0.25 root 3 and 0.5 times 6. Ladies and gentlemen, how many of you would have done this whole problem all over again? You know, why would you waste your time? Value your time. Use it wisely, right? Why would I waste my time doing all that work again? So now I'll get about 0.64. Wow, interesting. There's 0.64 square feet for each of these tiles. So this is 0 point. And this is going to be inches squared, sorry. Okay? So like imagine you had square tiles, you know? If they were all 1 square inch, it would take 2,160 to cover this surface. But since these are hexagons, they're a little bit smaller, actually. They end up being a little bit smaller than 1 whole square. So it should be as no surprise. It should come as no surprise then that when we take the original area, 2,160 square inches, and then divide by 0.64 square inches, we get. And actually, what am I doing? I don't want to type in just 0.64, do I? I want to type in the whole number for full accuracy. So I'm going to arrow up and grab that whole number, and I get 3,325.5-ish. This is approximately 3,325.5. Interesting. And this is not, now notice what happens here. The units cancel. There is no unit to this number. This is, I guess so. This is like number of tiles, maybe, is the unit here. This is how many tiles you need. But, as I'm sure you know, maybe they only come in packs of like 10 or something. Alrighty? They're not going to sell just one of these square inch tiles. So let's say they come in packs of 10. Alrighty? For the purposes of the question. And just, guys, what I mean, like, this is the answer, technically, to this problem, because it doesn't ask you to specify. Okay? Let's say they come in packs of 10. Well, how many do you got to buy? You got to buy 3,330, because this rounds up, right? Divided by 10, or 333 packs. Alrighty. Interesting. So, I mean, obviously, this part of the question is optional. You know, I'm just saying, like, just to show you guys, we are only doing high school math. Obviously, if you were an engineer or an interior designer, there would be more depth to this. You'd have to calculate the price and wonder if that's in your budget and wonder if it's worth it per material or change maybe the shape from hexagons to something else because it was easier to follow, right? Maybe it looks ugly, and then you do the demo and it looks ugly and you want to change it to another type of tile, right? Who knows? Alrighty. So, Jade and Littleman. Please try the next page as well. I'll see you in the next video.